Hello, everyone, and good morning. My name is Eric Lanz. I'm an SDK engineer with Embrace. I've been doing software engineering for 16 years and iOS engineering for about 11 now. I've worked in the gaming, finance, healthcare, and communications industries, and I was a member of the WatchKit team at Apple for 3 years. A fun fact about me is I once demoed an iPad application to Anish Chopra, the Chief Technology Officer of the Obama administration. But today we're here to talk about game developers and what they can teach us about application architecture. So first, we're going to answer that question. What could a game dev have to offer us, the enterprise mobile developer? We'll talk about some of the challenges of real-time gaming applications versus the event-driven apps that we usually work on. Then we'll go over 3 architectural patterns. And finally, I'll leave some time at the end for questions and answers. So what can we learn from game devs? Are they really just reckless cowboys slinging code into production and hoping for the best? Well, that's not really true anymore. The modern game has way too much money behind it to be doing anything like that. Modern gaming studios have full architecture teams with full-time architects that help the rest of the developers understand the patterns that they use and make sure everyone is sharing patterns and knowledge across the studios. So game developers think about architecture just as much as we do. But where did they learn these techniques? Well, often the architectures that they use are part of the engines themselves. So some of the patterns we're going to go over today are a major part of how a gaming engine works in the first place. So what do I mean by a real-time application? Well, I'm not talking about the flight computers that are in the space shuttle. Those are real-time applications. But in this case, I'm talking about a game that updates its simulation of the world a certain number of times a second. So most games aim to update at 60 times a second. That means regardless of whether the user is touching the screen or not, the game is always updating and moving. You might notice some animations in the background or even enemy players moving around, even though you're not touching the screen. We use heavy engine software like Unreal or Unity to power this kind of interaction. We start with much larger teams. Major games often begin with over 100 people involved in production and grow from there. We're targeting a monolithic release with a huge marketing budget behind it. When you think about the latest Call of Duty or Assassin's Creed game, those PR teams started months in advance building hype for a certain launch date. The team building the game has to have that game on shelves on that date. There's no room for slippage. On the other hand, the applications that we work on, we think of them more as event-driven apps. And what I mean by that is the UI typically only changes when the user does something or a notification arrives. So an event happens. We use lighter weight frameworks like UIKit or React Native. Now, you might laugh when I call UIKit a lightweight framework, and I would agree with you. But consider this, the smallest UIKit app you can make is about 5 megabytes. On the other hand, the smallest Unity app you could make is going to be about 50 megabytes. So there's an order of magnitude difference in the weight of the frameworks involved. We typically work with smaller teams. The largest team I've ever been a part of for a mobile app capped out at about 50 people if you include, all of the producers and artists and everyone. On the other hand, most AAA games are starting with a team of hundreds. Finally, we have a continuous release cycle to work with. And we have launch dates too, of course, but we can do gradual rollouts, 1%, 2%, 10%. We can use feature flags to hide things, and we can update in production much more easily than a game can. So now that we understand the difference between the two apps, let's talk about some of the specific challenges that game teams have to face and the patterns they use to solve them. First, your game usually has too much work to do in a period of time. And the period of time we're talking about in a game is a frame. If your target is 60 frames per second, you only have 16.7 milliseconds to render that frame. Usually you want to do more AI and physics work than you can do in that period of time, so we have to use a pattern called multiplexing to split up that work across the frames. Another challenge is scene complexity. Think about the last game you played and how many objects were moving and changing on the screen at once. Typically it's tens of thousands of objects in the scene at any given time. Contrast that with the apps we work on where 100 views on screen would be a lot. More than 100 views and UIKit might not even be able to keep up anymore. We use a pattern called state machines to help us manage this complexity. And I'm going to teach you about that. Finally, we have huge teams and strict timelines. We need to be able to add contractors to our team quickly and let them be productive without a lot of coaching from the rest of the team. In order to do that, we need to use a specific architectural pattern called the entity component system. And I'll help you understand that. Before we dig into the patterns, I want to explain what I mean by a design pattern. Now, chances are you're familiar with this one, the model view controller pattern. It's built into the frameworks we use. UI view controller is an example of the view controller from this pattern. Design patterns are a pre-built solution to an architectural problem with your code. Are you configuring objects all over the place? Well, why not use a factory pattern and vend those objects from a single location in a pre-configured way that you can test it and control in one place? That's a pattern. Do you want a common place in your app to store shared state? We call that the singleton pattern. Apple gives us the UI application delegate as an example of this pattern. And then if you have these data concerns leaking into your UI, a model view controller pattern is how we solved that for years. Design patterns simplify your application. They make it easier for you to code features and to understand how those features work. But they also help other developers to read and understand your code. If I open a new project and it's using these common design patterns that we all know, I automatically have a leg up. I know how that application works, generally, without having to get a bunch of coaching from the engineers who built it. So now that we understand all that, let's dig into the first pattern. I call this multiplexing. Multiplexing is taking a bunch of long-running tasks, breaking them up, and then running them in an optimal order. And if you remember, the problem we're trying to solve by doing this is we have too much work to do in a fixed period of time. So the way we usually handle parallel processing in mobile apps is we take all the tasks we want to run, we call start on them, and we kind of hope for the best. And the operating system will do a good job in most cases. A modern mobile operating system has scheduling algorithms, time slicing, it can preempt threads, it will figure things out, and generally it'll get all that work done pretty quickly. But it doesn't know everything you know about your work. Often we know things about the work we need to do that would help the operating system to schedule these items better. Multiplexing is a way to do that. Instead of thinking of the work you need to do as one long task, break it into smaller pieces and run only one piece at a time. When worker 1 has had a fixed time to run part of worker 2, then worker 3, and round robin back to worker 1. In this way, you're balancing the work you need to do in a single parallel track. You won't have any contention between the processes, and things will happen in the order that you control. So where would you use this in a mobile app? Well, startup is a perfect place. I mean, think about the apps you work on. You might be starting 5 or 6 different third-party SDKs in did finish launching. Do you just call start on all of those? Are they all creating their own threads, making network calls, accessing the file system? Well, all that activity is very contentious, and the operating system is going to do its best to schedule it, but if you know where these things are going to deadlock, why not schedule them instead? Apple gives us an awesome system called NS Operation Queue, which is a great way to manage your startup procedures. Put each SDK into an operation, put those into a queue, and now you can manage how many run in parallel, what their dependencies are, and you'll know when they're done. In the same way, when your app goes to the background, you only have 30 seconds to finish your work before your app has to pause. So here again, you have a fixed period of time, and you might have more work to do than you have. Multiplexing is a great way to manage that and make sure you can stop that work when you run out of time. Migration code, when we upgrade versions, sometimes we need to load our core data model into memory and then write those objects back out with some different properties. Well, your user doesn't want to sit there and wait for you to do that. Why not use multiplexing to run that work in the background, manage the CPU it uses, and let your user use your app? Processing images and videos, the same thing. Think about when you load a table view and you're scrolling through it. Are you just requesting all the images the user wants? What if they scroll really fast? Do you queue up hundreds of image requests? Use multiplexing to manage the number of images you're requesting in parallel. Your users will be a lot happier. So there's got to be some downsides to this too, right? But let's talk about that. So some of the pros of multiplexing, you get that controlled execution. You now have control, not the operating system. If you want to stop this work, you can. You don't have to wait for this long task to be done. You can set resource budgets. You can do background activity and say, if the CPU usage gets over 10%, pause this activity. And if it's less than 10%, maybe run 2 activities in parallel. You lower the contention on the system. You'll get predictable performance again. If your user scrolls too fast, you're not going to suddenly drain their battery with hundreds of image requests because you control it. And you can scale up or down for the hardware you want to run on. This is a big part of how the same game can run on a PlayStation 5 and a Nintendo Switch. They'll just do more AI work, more physics work in a frame when they're on a more powerful system, and less when they aren't. Now, some of the cons are you need to be able to slice that work. So you need to think about how you're going to cut that work up into pieces that can all be run in parallel or in sequence. The value of doing that has to outweigh it. So if you think about adding a filter to a video, if that's the main thing your user's doing, multiplexing might not be the right answer because your user wants that to be done as quickly as possible. In that case, let the operating system optimize that work for you. But when you're thinking about background activities or things the user doesn't necessarily care about, multiplexing is a great fit. And this technique will increase your code complexity, but you get all the benefits in the pros column, so I think it's worth it. The second pattern I want to present today is called state machines. Now, I'm sure everyone listening here has heard of state machines and probably has some idea in their head of what that is. I'm still going to go over it in a little bit of detail because I want you to understand exactly how I think about state machines in regards to UI work. So first, what is a state machine? Well, a state machine is a system that defines what elements of your UI are active at a given time and how the transitions between those states happen. And if you remember, the problem we're trying to solve is scene complexity. When you have 10,000 objects moving on the scene, it's too hard for you to think about the states of all of those at once. So we need a pattern to simplify that. To help you understand what I mean, let's walk through a pretty typical example of a view controller I think we've all made. I've coded a login view controller 10 or 20 times in my day. It always starts simple. You're just going to need a username, a password, and a login button. Oh, but we need to be able to register new users, so well, let's add a register button and an email field. And of course, we want to be secure, so we're going to add that two-factor authentication feature too. And right, our users need to be able to get help and support or recover their passwords, so we're going to need those buttons and fields as well. You know, quickly, this relatively simple view controller now actually represents maybe 4 distinct states that it can be in. This view controller likely has animation code and showing and hiding code for these fields. You might have to hook these up like this. You're going to have to hide the password when you're registering a new user. Well, the help stuff's going to kind of cover everything up. Quickly this devolves into what we think of and call spaghetti code. You open this file and you can't reason about it anymore. You can't just read this code and see what it's going to do. Instead, you feel compelled to run it. Often when I join a new project, the first thing I do is run it in the simulator to see how it works. Well, that's not very efficient. If every contractor you bring into your project needs to be able to run the entire application or the full game to understand it, well, that's going to slow you down. State machines can help. If instead of thinking of this class as one big interconnected bowl of spaghetti, we can separate things out into states. We can define a login state, and when we're in the login state, we only need to think about the username, the password, and the login button. That's it. We can ignore everything else because we know we're in that state. When we're in the register state, we only think about these fields. In two-factor, these fields. So you can see how the state machine has already simplified what you need to think about for a given state of your app. But it can do even more for you. The state machine also defines what transitions are valid. So when a new user enters your app, they need to register. So we will code and test an animation to move from the login state to the register state. And we'll code and test an animation to move them back to the login state when they're done. No user will ever move directly from register to two-factor authentication. The state machine can expressly prohibit this transition from happening. We do not need to code or test any animation related to this transition. Instead, we'll code this one, the login to the two-factor authentication. That's the transition that a user should take, and that's the one our QA team should test. So where can you use this in your app? Well, any complex user flow. So the login example is a pretty obvious example. I just went over that. But checkout and cart management is another place in your app where often the UI logic gets very complicated, and straightening that out with a state machine can help a lot. You can also layer state machines to reduce the complexity further. Think about a game that needs to control a flock of birds flying through the sky. Each one of those birds can have a state machine controlling its animation. Is it taking off? Is it flying? Is it landing? Each bird has a copy of that machine. But the entire flock also has a state machine describing its behavior. So now I can reduce these 100 birds to one state machine. I can say that flock of birds is taking off, or that flock of birds is flying. It's a way to simplify what I need to think about when I think about what's going on the screen. The state machines are also an excellent debugging tool. If you add logging to the transitions in and out of any given state, well, now you have a map of the path the user took through your app. You know exactly how they went from state A to B to C. Your QA team can use that to reproduce their issue and help you fix it faster. So state machines reduce the complexity of your app. They define the testable transitions. The state machine pretty much writes the QA plan for you. This is what you have to test. It also tells you what you don't have to test. If a state transition is impossible, why test it? This will increase the confidence in your software for everyone on your team. It's a major reason that game teams use this pattern is because artists and producers can talk about the game in its state terms. They know what a login screen is. They know what a checkout screen is. They might not know the details of the AI system or the physics system, but they can talk about the states. Everyone can reason about the application because they can think about it from this abstract point of view, the state point of view. There are some cons though. Well, the game engines have amazing support for state machines. Our mobile platforms don't have any built-in tooling for this. You're going to have to write your own. Now, I see that as a pro because now you get to learn how to write a state machine, and also you get to optimize it for your use case. You can add that debugging logic that I talked about and get those powerful features. The state restrictions can be difficult to break later. Remember, we said we wouldn't allow a user to move from register to two-factor. If we later decide to allow that, well, we probably coded some of those assumptions into the state machine. So we're going to have to unpack that and retest all of those transitions again. I actually look at this as a pro. If your product team knows that it's going to be harder to break transitions later, they're going to put the effort in to get the transitions right at the beginning. So you're going to get better product design by using a state machine architecture. And finally, a warning. Dead-end states are worse than crashing. Any game developer can tell you this. The worst case is to leave the user in a place they can't get out of. So when you're designing your state machine, put it on a whiteboard or on paper and make sure there's always a path out of every single state, because users get very frustrated when they hit a dead end. All right, let's talk about the last pattern I have for you today, entity component systems. An entity component system, which we abbreviate as ECS, is a way to get the benefits of inheritance without the cost of using subclasses. And if you remember, the problem we're trying to solve here is huge teams and strict timelines. We need to be able to onboard 10, 20, 30 contractors and have them be productive in our code base. So let's talk about what I mean by the benefits of inheritance and the problems of subclassing. So I'm sure you've all seen this class, the default table view cell. This is the base class we use for table view cells in most of our apps. Now, almost everybody goes and makes a subclass of that right away for their use case. Maybe a two-label table view cell, which is a subclass of the default table view cell. But this one has two labels. The first label is drawn by the base class, and the second label is drawn by the subclass. Later, we may add one that has a photo on it as well. But again here, the two labels are drawn by the subclass above it, and the photo is added by this class. And then later on, we may need to add something like a product view with a description to the cell. Well, if we subclass it again, now we have a hierarchy that's 4 deep. And the problem with this is if we need to change anything in that hierarchy, we need to coordinate our checkouts with the rest of the team. I'm sure everyone listening has suffered through this with Xcode project files, but contention on a source code repo can be a real productivity killer for your team. If you use a subclassing strategy like this, you're guaranteeing you're going to have contention on the base classes. So what's a better way? Well, if we think about this problem from an entity component system point of view, instead of putting any labels on the default table view cell, we're going to put a collection there instead. Now, this collection knows how to draw any components that we add to it. Then we add an algorithm to the class that will lay out those components in any way that we want. But the base class itself doesn't specify what components to draw or how to draw them. It only specifies the interface that a component has to conform to in order to be drawn. And it specifies the interface that a layout algorithm conforms to in order to control the position of the components. Now we can hire contractors all over the world to code different components for us that conform to our interface. Someone can build us that label we wanted, someone can build the photo, someone else can build the product. None of these people have to talk to each other. None of these people have to contend on a single source code file. They'll code to our interface, they'll submit their final tested component, and we'll use it in our class. We'll have a separate set of contractors build us our layouts. Maybe we want a flow layout like the web where things, flow in a row and then wrap to the next line. We also would love to have a grid layout like collection view uses. where we have fixed cells. Maybe we want a fixed layout too, where we can specify the CG recs that we want to use for each of the components we'd like to draw. Well, now we have a pretty powerful system here. We can make any cell we want. We can make that default table view cell. That's easy. That's a label with a flow layout. Two label cell, just as easy. I can add a photo. It just works. Let's switch that to fixed layout. I hope you can see the power of this system in action. We can create cells that our product team never even thought of. And they're all going to work fine because we tested these to their interfaces. So where can you use ECS in an enterprise mobile app? Well, view composition, like I just showed you, is the natural fit for ECS-like systems. In fact, you might not think of this, but UI collection view, which Apple gave us a few years ago, is an example of an ECS system that Apple built and gave to us. I think everyone can see the power of that kind of flexible composition logic and the different types of views that you can make. But that's not all. Processing images is another great place to do this. You know, why have this complex subclass, base class hierarchy for your filters? Why would you have a separate subclass that's, you know, apply a blur and a color, and then a different one that applies a blur and a border? Like, why not code 3 components, a blur, a color, and a border? Now you can combine them in any way you want. Your users are going to have more fun using your app if you use this system rather than a hierarchy. Now, ECS is also even better when combined with a state machine. If you think about the login view controller we went over in the previous pattern, imagine if each of those fields I was talking about was a component. Now the state machine can expressly disable components that are not valid in a given state. It's very powerful. And then anywhere you have a large file with source code contention, that's what ECS is built for. Switch that file from hierarchies to composition, you won't have contention anymore. So each component that you build is going to be simple. We have a simple interface, maybe only 3 or 4 methods it has to conform to. Components can be attached to entities in unique ways. As we saw, we were able to make table view cells our product team never even thought of when we coded this as an ECS. The development of each component is independent. You give your contractor the interface, they give you back the component code and a unit test suite. Composing well-tested pieces in new ways is always safe. When the interface is that simple, it really can't break. Now, some of the cons are, again, we don't have any built-in tooling, whereas engines like Unreal and Unity are essentially entity component engines. That's not the case on mobile platforms. So again, we're going to have to build this system ourselves, but I see that as a pro, because you get to learn how it works and you get to optimize it for your use case. The initial dev time to build an ECS can take a little bit longer. It's not quite as simple as a state machine. But I hope you can see from the example I gave the power that you're going to get if you invest that time. And then finally, another warning. Having built a few of these systems myself for mobile apps, I can tell you that you can go too far. And if you do, you're going to end up rewriting a system like CSS. And at some point, it's probably better just to use CSS. So make sure when you're coding this that you don't have too much fun and go too far. Rein it in for your use case and make sure it fits with the app you really need to build. So let's take a step back. We've gone over a lot of data. I've shown you 3 really big architectural patterns. You might even be a little scared right now. I want to take that away. This shouldn't be a scary thing. Like I was talking about with the flock of birds and the single bird having a state machine on for its animation, you can add a state machine to a single button in your app. And you'll already start to see the power of these patterns. Start small and grow from there. The next time you need to code a table view cell, consider using composition instead of inheritance. By starting small, we can see the power of these features in our projects and grow from there without having to invest a lot of time up front. So let's summarize what we've learned today. Well, games have some unique challenges due to their real-time nature. There's complex scenes, too much work to do. Game teams use architectural patterns to reduce that complexity and solve those challenges. Those same patterns can help reduce complexity in the event-driven applications that we work on. Good architecture helps your app, but I hope you can see it also helps your team. A major reason that game teams conform to these patterns is so they can scale up and down their teams quickly. When you hire a game engineer, they know what an ECS is. They know what a state machine is. And finally, we should be sharing more between industries. I'm an engineer who has worked on AAA games and major mobile apps, and I've gone back and forth a few times in my career. I can tell you there's a lot to learn from each side. I hope in the future we can share more between these industries and learn from each other. So that's all I have.